show again the QR.
All right. Okay, now the session is recording. All right. So thank you for reminding me. Okay, so this is the attendant. Okay, let me share you the lecture note. Okay, this is the last yesterday lecture note where we managed to fill up until the example of this part. Okay, where we need to substitute all the value into this equation. All right. To recap first, all right, this is the example 1 where the water at 20 degrees Celsius flows between two reservoirs at the rate of this. Sketch the HGL and EGL. What's the minimum diameter? This is the design part. If you remember, okay, if you remember our last session where we have category under category number, do you still remember when we deal with the major losses? Okay, can you see the major losses where we need to provide the diameter when it is given the Q, the flow rate, the relative roughness, the velocity and the heat loss. Okay, this is category number 3, which is the hardest part where you need to design. All right, you need to provide, you need to propose the diameter that will protect the pipe from cavitation, right, for this case. So this is fall under category number 3. Okay. From here, the question asks, what's the minimum diameter? Diameter of what? All right, you need to provide to avoid the occurrence of cavitation. In order to avoid cavity, the local pressure must be, okay, must be more than vapor pressure. It is, if supposing if this is less than the vapor pressure, the cavitation will occur. All right, so let's say 0.1 is the atmospheric pressure, but when we deal with the cavitation, we must use the absolute measurement. All right, because the quantity that can give the indicator whether it is cavity or not, it depends on the absolute vapor pressure. So from here, when you refer table, and you will find out that the absolute vapor pressure at 20 degrees Celsius should be 2450 Pascal. This is absolute. So when it is absolute, right, you need to use the absolute measurement, the absolute unit. So the pressure one, which is supposed at the atmospheric pressure, where we can cancel out actually before this, but once this is absolute, we must put the value of atmospheric pressure. Okay. So P1 over gamma, we rearrange the equation. This is at point 1 to point 2. Alright. So at point 1 to point 2, we deal with the velocity at point A and velocity at point B to reach the point 2. Okay, that is why we need to calculate the velocity at A first. You can see here. We need to find the velocity at A first and then velocity at B in order to find the major losses, which is the friction along the pipe A and the friction along the pipe B. You can see F, right, from A and F, and for B, okay, it gives you the equation. Alright, so because of this, you just substitute the value. Alright, the pressure 1 over gamma, this is the energy equation. Alright, this is B1 squared over 2G plus P over gamma plus Z equal to V over 2G plus P over gamma plus Z2 plus head loss. Alright, you cancel Z2 because the Z2 is at the datum point. So it is 0. And then velocity at the surface here, 1 is 0 because it moved very, very slow. Okay, and then we left P1. P1 should not be 0 because it is absolute point. Alright, we have to include the absolute. So with this, we have the head loss. We know that the head loss from point 1 to point 2, consider the major and minor losses. So we need to expand the equation of major losses, which is F LD L over D V squared over 2G. And the minor losses, which is summation of coefficient K V squared over 2G. You substitute all the value related to the losses in terms of the entrance coefficient, the contraction coefficient, alright? You rearrange the equation with respect to the VB and respect to VA, substitute the value. So now I would like to continue to substitute the value from here. Okay, do you have any questions so far? Okay, so you try to substitute. This is a VB. Okay, 1 plus K contraction. Okay, let me check the table. What's the value of K contraction? Okay. So from here, K contraction. Yeah. Okay. So 1 plus K contraction, in this case, it is 0.25. This you can refer directly from the table. Plus friction at B, which is unknown. And LB, the length of LB region is 20 over width diameter at DB, which is unknown as well. You can see this one, LB. LB, which is from here to here, is 20 meter. Okay. And then close bracket. Continue with P2. All right. What is the pressure at point 2? Anyone? What is the pressure at point 2? At point 2, the pressure. Okay. At this region, the pressure at this region. Anyone knows what's the pressure? Value of this pressure? Would like to try? We'll get 10 points. Anyone there? Any call upon Abdul Rahman Hani Al Said. Are you there? Abdul Rahman Hani Al Said. Okay.
Doctor, is it 0?
Your name is Abdul Rahman Hani Al Said?
No.
Oh, okay. Okay. Ammar Ali Al-Washi, are you there?
Yes, doctor, I'm here.
Okay. What's the value at the point 2? Pressure at point 2?
It will be the minimum, right? So probably at point 2.
What there?
At point 2.
Yes, at point 2. What's the pressure at point 2? The value of pressure at point 2?
Doctor, may I try?
Okay. You may try.
At point 2, the value should be the pressure of minimum 24,450 Pascal.
Yes, perfect.
I said the minimum.
Yes.
I said the minimum.
Okay. It is the minimum vapor pressure. It is P minimum that is equal to the vapor pressure. You said 2450, right?
I was looking for the P vapor.
Because your name?
Ammar.
Okay lah, Ammar.
I said the minimum, but I was looking for the value because I couldn't
Ammar,
find.
you got 5 point lah.
Okay.
Okay, Ammar, your section.
1.
Section 1, okay, 5 point. 5 point. Okay.
Thank you.
The one after Ammar?
Aina.
Aina from?
Aina, give me.
Section 1.
Aina. Azhar.
Yes.
Okay, 10 point for you. Because first, you got correct of P minimum. Second one, you mentioned the value. Okay,
Give
this
me,
is the value.
Give me her 5 because I said the P minimum. So I should get the 10.
You said P minimum, but not said the value.
Okay.
Okay, so I'm looking the value here. So the value here, P2 is 2450. Okay. So that means, okay, 24 and gamma is 9810. And then continue. This one plus VA. VA found already 1.91 squared over 2G, which is 9.81. And K entrance, which is from the 0.5 plus FA. FA we found already, which is 0.022. Okay. 0.022 LA is 30 meter over diameter at point A at the region A 0.2. Okay, you solve this one. Okay. And then you will find out that, okay, let me check first. Okay. Yeah, this one you try to solve. Okay. Try to solve, it will be 9,600 equal to, okay, equal to, okay, So okay, let me write it down. This one. Okay. So this one basically you require to solve lah. Alright. For me, I think okay, you can use your calculator. You know already using your calculator. You to by define dB as the A, FB as the B. Do you know how to make the to substitute using the calculator? Anyone? Do you know? For example, you use mode, okay, and then go to equation. You type mode 4 times, and then go to equation 1, okay, and then choose unknown. Okay, go to unknown. How many unknown do we have here? Anyone? We have 1. We have unknown 1, dB and FB. So we choose unknown 2. Okay. Sorry, it's not like this.
Sir,
Yeah. Yep.
shouldn't we arrange it first before we put it in the calculator for finding unknown?
Yes. Supposedly, you arrange nicely. This is the equation. For example, you try to solve this one. Okay, the first left side, you will get 98600 will be equal to, alright, for example, you have the value of this dB. Okay, and then you have the value of this one. Okay, let me calculate for you. 0.0764. Alright, the power of 2 divide with 2 divide with 9.81. Okay, so you have 2.975, the power of 10, the power of -4. Alright, this is the -4 because this is the power of -2, and this is 2. Alright, and then this is 1.25 plus FB 20 over dB. Okay, and then solve this one. Okay, 30 over 0.2 multiply with 0.022 plus 0.5 multiply 1.91 squared over 2 over 9.81. Okay, this one. Okay, this one to be 0.7066 plus this value 2450 over 9810. Okay, so you will have the value plus 0.9563. Okay, so this value you can move, move to the left side. Alright, 98600 minus this value. So you'll get 98599 equal to 2.975 multiply with -4 dB -4 1.25 plus FB 20 over dB. Okay, so this value require try and error. So first, I would like to let's say, okay, let This is not clear. Okay, I want use try and error method. Okay, first you try to substitute let. Okay, you try the first at d b equal to 0.1. Okay, and then you will find out that the relative roughness E over dB equal to 0.0026. And then you will find out that the Reynolds number at B is 7.6 multiplied with 10 to the power of 5. And therefore F, okay, here should be 0.026. Okay, why Reynolds number related to this one? You can see here. Reynolds number at section B, okay, relies on the dB. So you substitute dB value, you will get the Reynolds number. So from Reynolds number and relative roughness, look at the Moody diagram. You will find out that the Moody diagram to be 0.026. So you have the FB, you have the diameter. You try to substitute. Okay, I try to substitute. Okay, you will find 98599. Okay, is this equal when you try to substitute? So I try to substitute this one. It will be 12500. It will be 97700. Okay, do you think this is accurate? No, right? So you have to repeat again with another try and. So now let's put the diameter at B equal to 0.09 meter. Okay, and then you will find the E over dB to be 0.0029, and then Reynolds number at B to be 8.4 multiplied with 10 to the power of 5, and therefore FB, look at the Moody diagram. Okay, the Moody diagram to be 0.027. Substitute the value 98599. Is it equal? Okay, try 0 plus 9. Okay, it is 110,000. Okay, so we see that 0.1, okay, this value, we see that this value, okay, upon you substitute the equation into the equation, the value is significant. It is quite different. Okay, when you try to substitute this value, it is almost close, right? This is 98,000. This is 110,000. Okay, so in fact, the value of 0.09 meter is the only slightly too small. Consequently, to be safe, we must select the next larger pipe size, 0.1 meter. If there were a pipe size of 9.995 millimeter diameter. Okay, so for this case, we can see that okay, 0.0. So this case, okay, it is this way. Okay, in manufacturing company, all right, when you go to the shop and I say I want to buy this pipe diameter, okay, it is likely it is not available. with this number. So we must take more than this number, alright? Because this is not the standard number. So we might take 0.1 meter. Why we must take 0.1 meter? Because the larger the pipe diameter, okay, it will. Anyone knows why we should select larger pipe diameter from this value? Anyone knows? Okay. If we select larger pipe diameter, do you think the pressure is increased or decreased? You can see from this
Decrease.
diagram. You can see from this diagram. From this section to this section, increase in pipe diameter. What do you think of the pressure? Hydraulic pressure.
Decrease.
Decrease.
Increase, right? So your intention to avoid what? What kind of nature phenomena? Your intention to avoid the occurrence of cavitation. So if your selection is less than 0.09 meter, okay, that means the cavitation will occur. So you must select the pipe diameter more than 0.09 meter in order to avoid cavitation. The increase in the pipe diameter will increase the pressure. You can see here the pressure increase. Okay. So in this case, in order to avoid the cavitation, okay, this is the critical value 0.09. So you must select 0.1 meter, okay, to avoid cavitation. Okay, less than this value, less than diameter this value, cavity will occur. It will happen. Alright. So I think that's all about this example. Okay, we proceed to the last part. Okay, the simple pipe system with the pump, with centrifugal pump. Alright, if the flow rate pump is not given, okay, you can see if the Q is not given, it is not straightforward question. Remember that this one, as I mentioned before, this one, if Q here is not given, that means this is fall under category number 2, where you need to find the Q. Okay, the previous example, we need to find the diameter, where we try and error. Alright, we substitute 0.09, right, and we substitute 0.1. We see the value almost close to the left hand side, and then we choose that value. So for this case, this is fall under category number 2, which you need to find the Q, the flow rate. So if the flow rate of the pump is not given, it is not straightforward. Alright. So the head produced by the pump and the efficiency depend on the discharge. So from here, in order to solve this issue, this problem, we need the pump characteristic curve, right? So the pump characteristic curve relate to the Q and the head pump. So this is the equation. Head pump equal to the coefficient 1 plus C2 coefficient 2 Q squared. Why this is the characteristic curve? You can see this is the characteristic curve. Okay, this is the system demand curve, and this is the head of pump. This is, you can see here, it is quadratic. Head of pump equal to C1 plus C2 Q squared. Alright, so the primary axis is the head of pump. The secondary axis is the efficiency of the pump. Okay, anyone, do you remember what the pump? The formula of the pump, head of pump is equal to, remember, work rate of the pump over mass, flow rate, gravity. When we have the efficiency of the pump, it should be input of the pump. Okay, so head of the pump, basically, this one go at the side. Work pump, efficiency of pump, mg. If we want to find the work rate of the pump, basically it is reverse. Head of the pump, mg over efficiency of the pump. Okay, this is the equation. Remember the equation of energy. Okay, this is the pump characteristic curve, right? And then this is the flow rate. This is the standard version, right? So this is the intersection between the head pump with the system demand curve. At this point, basically the operating point for your pump. And with this, we can get directly the efficiency. Okay, so in order to know how to use this, better we try this example number 2, all right? So basically, it is the same. We have the system, we have the pipe here, and then we have the pump, all right? So estimate the flow rate in the simple pipe system if the pump characteristic curve provided there. Our requirement, okay? So first, let's analyze this one first. Okay. Okay. So for this case, we will assume that the Reynolds number is sufficiently large that the flow is completely turbulent. Okay. So for this case, alright, the velocity is not given. And the question not give you the flow rate. Remember, supposedly, many questions will give you the flow rate Q. But sometimes, if the flow rate is not given, you can see here, if the flow rate Q is not given, it is not straightforward. Because you need to find the velocity. From velocity, you get the Reynolds number. From the Reynolds number, you need to find the friction, all right, along the pipe. So from here, you need to assume that the flow is completely turbulent flow, right? Assume flow completely turbulent. All right. So let me put the chart here, the Moody diagram chart, so that you can make a reference. Okay, this is Moody diagram. Okay. When you look at it is completely turbulent flow, you can find from this chart. Can you see? This line refers to the completely turbulent regime. So you must use this line. Okay. And it is given that in order to find the friction factor F here, you need to have one more parameter, which is relative roughness. So the relative roughness E over D is, you can see, this is rough iron pipe. You look at here, rough iron pipe 0.046 millimeter. Okay, so 0.046 mm divide with diameter of this pipe, which is 200 mm. Okay, so you will get the answer to be 0.00023. From here, all right, look at the Moody diagram, 0.0023. Where is 0.00023? Okay, I try to look at 0.0023. 0. This one. Okay, this is almost this one. Okay, this is 0.002. This is 4. Okay, this is 0.3, 0.0003, and this one very close. Okay, make the line smooth. Okay, all right. Okay, so when it is completely turbulent flow, you must use this region, the straight. I call it as a horizontal straight line. So this horizontal straight line, supposedly here, this region is completely, so you must use this one. So directly here, okay, you will find out that your F here, suppose from the question it is 0.014. Okay, it is accurate. So you get the F friction factor, okay, to be 0.014. Okay. The energy equation, okay, at point 1 and point 2 here, point 1 and point 2, I want to use my energy equation. So P1 over gamma plus V1 squared over 2G plus Z1 plus do we have the pump? Yes, we do have the pump. So include the work rate of the pump over M dot G, okay, equal to P2 over gamma plus V2 squared over 2G plus Z2 and plus heat loss. Okay, remember that the heat loss considered by major and minor losses. So we start with minor losses first. The summation of K V squared over 2G plus the major losses F L over D V squared over 2G. Alright. So here we have how many K? Anyone? How many K? What type of K here? From our chart, from our diagram.
3 only.
We have 3. Are you sure? Which number 3?
Is it the entrance and then the heat pressure?
Entrance. Okay, the entrance we have the loss. We call as a K entrance. At the exit we have the loss, K exit. One more. You said 3? No? Or 2? Okay, basically it is only 2. Alright, K entrance and K exit, because we have sudden change of cross-sectional area. Right. So from here, P1, okay, pressure at point 1, this is not involve cavity. So when this is not cavity problem, we can use the gauge pressure. Okay, so the gauge pressure for atmospheric is 0. So cancel this one. And at point 2, 0. The velocity at point 1 and point 2 also 0. Okay. And this one basically is the head of pump. Okay, this is the power. WP work rate is the power, yeah. So from here, okay, you try to Z1 and Z2. Okay, so rearrange the equation. Head of pump. Okay, this one I try to simply head of pump. Okay, replace with head of pump equal to this one, yeah, head of pump. I try to replace with head of pump. is equal to Z2 minus Z1 plus heat loss. Okay. So head of Z2, what's the value of Z2? Elevation 90. Z1, Z1 is 90. Z2 is 60. So 90 minus 60 plus heat loss. So for this one, heat loss for the K entrance, we have K entrance plus K exit. Okay. We have plus, okay, all right. Okay, we have, I think nothing, only F, L over D, bracket B squared over 2G. Okay, because all these terms have the B squared. So this one I try to simplify. I factorize. Only left K entrance, K exit plus F L over D. So this one basically is the minor. And this one is the major. It is the same thing here. So I try to substitute. This is 30. Okay. Plus K entrance, refer to the table, you will find 0.5 plus K exit, which is 1.0, plus friction factor, which is this one, 0.014, L, the length of the pipe here, from this one to this one, 400, over diameter. Diameter, I believe it is 200 millimeter. So it is 0.2. Close bracket. Velocity. Velocity, do we know the velocity, anyone? Do we know the velocity?
No.
Okay. Okay, we do not know the velocity, right?
Or we can get the velocity.
Yes, correct. We
Yeah.
can get the velocity. Q equal to AV. Velocity equal to Q over area. But the flow rate is not given. But the area is given or not?
Yes.
Yes, pi r squared. This part is, okay, so just substitute the value. Okay, velocity is Q over area, which is pi, diameter of the pipe to be, is the radius of the pipe to be 0.1. Yeah, this is half radius. We use the radius, not the diameter. And then this is, okay, sorry. This is squared, all right, and then this is bracket squared. You can see we have the power of 2 over 2g. Okay, you solve this one, you need to form this part. So head of the pump, it is like you form the pump characteristic curve. 30 plus 1520. It is almost the same like this, right? You remember? C1 plus C2 Q2. This one. So this is the, okay, pump characteristic curve. This is the system demand curve. Right, so it is almost the same. Okay, so from here, this equation you can see the system demand curve. Okay, the system demand curve. Why it called a demand? Because you need to put the value of Q. So this system demand how much power of HP. So and the characteristic curve HPQ of the pump are now solved simultaneously by trial and error. Remember, category number 2 and 3 require trial and error analysis process. Actually, the curve could be plotted the same graph as the characteristic curve. Okay, at the point of intersection, the operating point would be Q. So now we try and error again. Try and error. Okay, let's say Q is equal to 0.2 meter cubic per second. Where to get this reference? You can see from this one, from the given pump characteristic curve. Okay, we start with Q here 0.2. Okay, from this one, you try to substitute Q from your equation. Inside this, you will find that the head of pump for your equation, okay, will be 91 meter. But when you compare the head of pump from the chart, this is from the chart, yeah, from this graph. Okay, 0.2, the head of the pump should be around 75. Okay. Curve. This is 60, this is 70, 75 meter. So is it accurate? It is not accurate. So again, do you need to do the try and error analysis, anyone? What do you think? Do we need to do the try and error analysis again in order to match the value of HP and HP of the characteristic? Anyone?
Can try one more time.
Yes, perfect. We can try one more time. Okay, Q. Let's say we try the Q to be 0.15 meter cubic per second. Try to substitute in this equation. Okay, you will find the head pump to be 6. Okay, pump of yours to be 64 meter versus 0.15, this one. This one. Okay, it is to be 75. Sorry. Pump. Okay. Yeah. Okay, 0.15. Okay, this one, yeah. 0.15. Okay, this is our HP. This line, not this line. This is efficiency line. This one. Okay. From this one, you will get it is around 75 again. Sorry, it is around 76 lah, more than this. So head pump of the characteristic to be 76 meter. So it is almost close, okay, compared to the value here. So try another one, last one. Okay, maybe this is the last one. Try 0.17. Okay, we try in between here. Try to substitute, you will get the head of pump to be, okay, 74. Versus the head of pump characteristic, you can see 0.17. 0.17. Which one? This is 0.15. This is 167. Maybe this one. Okay. Different color. In between here, yeah. Okay. So you will find it is 74. Okay. Sorry, it is 76 meter. So you can see the try and error until iteration 2 almost close to this one. Alright, so this is our solution. This is our solution where Q should be selected to be 0.17 meter cubic per second. Okay, from this Q, okay, we can get the, I think we can get the Reynolds number. Okay, you can see Q, we can get the Reynolds number from this V. Okay, we can get directly Reynolds number, which is D Q over AV. I believe this one, yeah. Reynolds number is VD over nu. So velocity, I believe you know, Q equal to AV, Q over area, diameter over nu. Okay, Q is 0.17, area is pi, R 0.1, okay, 0.1 squared, multiply with the diameter. I think it is given 0.2, okay, over nu, which is the kinematic viscosity at 20 degrees Celsius. You can see here, water at 20 degrees Celsius. I believe you remember the nu to be 1.007 times 10 to the power of negative 6. Okay, you will solve, you will get the answer is 1.08 multiplied with 10 to the power of 6. So do you think this is turbulent? Yes, this value more than 2000, our critical Reynolds number. So this is sufficient to cause the turbulent flow. So our validation is valid or not? Our assumption, anyone? Assume the flow is completely turbulent. So it is valid because we assume it is completely turbulent and the value is far away more than 2000. It is completely turbulent. So from this, okay, first we have, okay, estimate the flow rate. So we have estimate the Q equal to 0.17 meter cubic per second and find the pump power requirement. Okay, because of the major and minor losses, we need the pump power. So what's the pump power? Remember, power is W dot P. This refer to the pump power and the unit should be in watt. Okay, HP is the pump head. The unit is meter. This is not the pump power. This is the pump power, WP. So, how to get the WP? Remember that our correlation previously, head of the pump is equal to W dot, okay, this is pump power, work rate of the pump over M dot G over with efficiency of the pump, because pump is the input. Input should be at the denominator side. If it is output, it is at the nominator side. Okay, so from, okay, we know already mass flow rate is equal to rho Q. Okay, this is the equation, yeah. Mass flow rate is equal to rho Q, or I believe you know mass flow rate is equal to rho AV, but AV is a Q, so rho Q is the same here. Try to substitute here. Head of the pump over efficiency equal to work pump over M is a rho Q, a G. Rho Q is the gamma. Alright, we know that gamma is a rho Q. And then make the WP as the subject. So rho Q is a gamma. Will be Q gamma head of pump over with the efficiency of the pump. So Q substitute 0.17 and the gamma of the water is standard 9810 multiply with the head of the pump. What is the value of the head of the pump? Anyone? Okay, previously we select this one, right? The iteration number 3. What is our value for the head of the pump?
74.
74 is your calculation. 76 is the theoretical. So the best is in the middle here. Is in between. Okay, it is more accurate. So we must select the head pump in between this. Because your selection is in between, right? Okay, 75 meter. Over with efficiency. How to get the efficiency? Anyone knows how to get the efficiency? Is the efficiency given? Is it given or not given? Okay, efficiency is given, but you need to 0.17. This is 0.17. Okay, 0.17 here. I think using this. Okay, draw straight line and stop until the efficiency curve. This is efficiency curve and go to the right side. Okay.
74. 64.
It is around 65 lah. Okay.
65.
If you do it correctly. So 65% is 0.65. Okay, 0.65. So try to solve, you will get the value to be 198 kilowatt. That is the power requirement to overcome the major and minor load. Do you have any questions so far? Is it okay, clear to you?
Doctor, the only problem is the table is maybe the values I will get, it will not be same as what you expected because the table is not clear, the values.
Okay. Yes, the table, I advise you during the exam, they will give you the table, for example, this one, but you must be carefully choose the value of K. For example, all right. Okay, this one, definitely they will give you. For example, you can see our K here, K entrance and K exit. Okay, you look at here, our shapes, K entrance and K exit. So where is our K entrance? Okay, you can see our pipe exit. There is only one, which is 1. You can memorize, right? So what is the entrance? You need to be alert the shape. Okay, it is the square edge entrance 0.5. That is why you can see here the K entrance 0.5, the K exit 1. Okay, clear.
I'm talking about the other tables, the Renault table, and the values there. To get the values from the Renault table is a bit hard.
Oh, okay, so my advice, you need to practice more. Then you will know it is odd or not. Okay, so I give you this simple one. Okay, this is quite simple basically. Where you need to find, this is basically the straightforward question. Okay, I hope that your exam will be as easy as it is. Okay, so I think that's all for today. Okay, we already have 1 hour. 1 hour class. Okay, I hope you focus on your test number 2. Okay, be prepared at 8:40 p.m. Okay.